Welcome to the Deep Dive, where we unpack complex ideas to give you a shortcut to being well-informed. Today, we're embarking on a deep dive into the fascinating world of high-dimensional data analysis. Our mission, to show you how we can uncover hidden simplicity within massive datasets and why this is fundamentally changing scientific discovery. We're drawing our insights from a comprehensive source that brilliantly connects mathematical principles with powerful real-world applications.
That's right. And for researchers navigating today's data landscape, this shift is really critical. We're moving from an era where data was scarce to one where it's just overflowing.
Yeah, absolutely.
This profound change has been heralded as the fourth paradigm of scientific discovery, driven by advanced computing capabilities that allow researchers to manipulate and explore truly massive data sets in ways never before possible.
So let's dive into this. Our sources suggest that despite the sheer volume of what we call big data, much of it surprisingly contains simple low-dimensional structures. This feels a bit counterintuitive. How can something so big be so simple at its core?
It's a profound realization, actually. And it leads to a crucial insight that our source highlights. The premise that incomplete data include information. Now, this isn't just some clever trick.
Right.
It fundamentally challenges the traditional wisdom that, more data is always better. It suggests that focused strategic sampling can be just as powerful, maybe even more so, for uncovering the true patterns.
Okay, give us an example.
Well, think about something as common as movie recommendations. Lots of users have similar tastes, right? And many movies are similar in style. So even if a user hasn't rated every single movie,
Which nobody does.
exactly, the intrinsic complexity or dimension of the preferences is actually very low compared to the full table of all possible movies. This low dimensionality lets us infer the rest of their preferences quite accurately, even from an incomplete data set.
So the core of this deep dive, and really the central theme of our source material, is to demonstrate how we can bridge that gap between the sophisticated mathematical principles of these low-dimensional models and their practical real-world applications. And critically, doing it all through methods that are computationally tractable and scalable.
Precisely. That's the goal.
Okay, so at the heart of this entire field is what's called the pursuit of low-dimensional structure. What does that truly mean for someone, say a researcher, trying to make sense of complex data?
It means identifying the underlying patterns or inherent order in data that exists in a much simpler form than its raw, high-dimensional representation might suggest. And this concept is incredibly universal.
How so?
Well, it applies to everything from pinpointing the core dynamics of complex systems, like in scientific measurements collected over time, to understanding patterns in large-scale human-made systems. And critically, for researchers, it also enables highly efficient data acquisition. Meaning, you don't necessarily need to capture every single piece of information if the underlying structure is simple. You can be smarter about how you collect data.
That sounds like it could dramatically simplify a lot of research problems.
Yeah.
How do we actually go about identifying these hidden structures in practice then?
One fundamental approach involves what we call sparsity. A high-dimensional vector or signal is considered sparse if only a small, limited number of its entries are non-zero.
Okay.
For example, imagine a system of linear equations where there are far more unknowns than equations. Typically, this would lead to infinitely many solutions.
Right, an underdetermined system.
Exactly. But if you have the knowledge, or maybe a good assumption, that the true underlying solution is sparse, meaning most of its components are zero, you have a much better chance of uniquely recovering that specific desired solution from the multitude of possibilities.
So the goal is to find the sparsest solution among all the possible ones.
Ideally, yes. Mathematically, this involves minimizing the L0 norm, which literally just counts the number of non-zero entries in a vector. However, directly solving this is a computationally difficult problem. It's what we call NP-hard.
Ah, okay, so not practical for big problems.
Not directly, no. So a common and very effective strategy is to relax this to L1 minimization. This involves minimizing the L1 norm, which is simply the sum of the absolute values of the entries.
And why does that work?
Well, geometrically, you can kind of visualize L1 minimization. Imagine slowly expanding an L1 ball, which, in higher dimensions, looks like a diamond or an octahedron shape, until it first touches the feasible set of solutions, that point where it first makes contact. That often provides your sparse solution. It tends to hit at the corners, which correspond to sparse solutions.
That's a great visual for understanding the mechanism, but what determines if this L1 minimization actually succeeds in recovering that truly sparse solution we're after? It's not guaranteed, right?
Good question. No, it's not always guaranteed, but we know the conditions pretty well. Two key factors determine its success. First, how sparse the true solution actually is. The sparser it is, the better our chances.
Makes sense.
Second, how nice the measurement matrix is. This niceness is characterized by mathematical properties like the coherence of a matrix and something called the restricted isometry property, or RIP.
RIP, yeah.
Yeah, RIP. These properties are essentially mathematical guarantees that our chosen measurements faithfully preserve the underlying sparse structure, making recovery reliable. And the Johnson-Lindenstrass lemma is also highly relevant here.
How does that fit in?
Well, it basically states that a high-dimensional collection of points can be mapped into a much lower dimensional space while approximately preserving the distances between those points. This illustrates a profound idea. Critical information about low-dimensional structure can often be encoded with a minimal number of measurements and then recovered efficiently.
Okay, so sparsity helps us manage high-dimensional data, focusing on the few important components. But what if the simplicity isn't in individual points being zero, but more in the relationships between data points? That's where low-rank structures come in, right? A different kind of simplicity.
Exactly. Low rank is essentially the matrix equivalent of sparsity. For a matrix, its rank indicates its intrinsic dimension. Technically, it's the number of non-zero singular values when you perform a singular value decomposition, or SVD.
SVD.
And many real-world datasets naturally exhibit this low-rank characteristic. For instance, going back to our movie recommendation example,
Right.
the table of user preferences can often be modeled as a low-rank matrix, even if it's largely incomplete because, users haven't rated every movie. This specific problem of filling in the missing entries based on the assumed underlying low-rank structure is called matrix completion.
So it's like filling in the blanks on a partially observed table, but using this mathematical structure to guide you.
Precisely. And the remarkable thing is that finding the best rank approximation to a matrix, or completing a low-rank matrix under certain conditions, can be solved very efficiently using techniques related to SVD. This is widely used in applications like collaborative filtering, which is basically how many recommendation systems work.
Got it.
And our source notes that incoherent low-rank matrices, where the underlying structure isn't too aligned with standard axes, are particularly amenable to successful recovery.
Okay, so we have sparsity for vectors, low rank for matrices.
But what's truly fascinating, and where things get really powerful for real-world data, is that we often encounter data that has both low-rank and sparse characteristics simultaneously. The prime example of combining these is robust principal component analysis, or RPCA.
Okay, RPCA. That sounds like a big leap, combining both ideas. What specific problem does RPCA aim to solve?
Imagine a video surveillance feed. The background, which is mostly static or changes slowly, can often be represented by a low-rank matrix because its information content across frames is stable and highly correlated.
Right, the background doesn't change much.
Exactly. But then you have, say, people walking by, or maybe temporary occlusions like a car driving past, or even sensor glitches. These are sparse disturbances. They only affect a small changing portion of the image data at any given time.
Okay.
RPCA aims to decompose an observed data matrix, let's call it Y, into two distinct components. A low-rank component, low, representing that stable background, and a sparse component, so capturing those dynamic foreground elements or errors.
So it's like mathematically splitting the original video frames into the stable background image and then just the bits that are changing or corrupted. That sounds like a fundamental way to dissect complex observations.
Yes, precisely. The source provides a really clear visual for this. If you have a corrupted image matrix Y, maybe think of a base image with lots of random corrupted pixels scattered on it.
Like salt and pepper noise.
Sort of, yeah, or maybe larger blotches. Mathematically, Y can be seen as the sum of a clean, underlying structured low-rank matrix, low, the original clean image, and a sparse noise or foreground matrix, so just those corrupted pixels or moving objects. RPCA tries to recover both low and SO from Y.
And the power is in getting that clean, low-rank part back.
Exactly. What's truly remarkable about RPCA is its ability to disentangle these complex, messy, real-world observations into their fundamental, simpler components, essentially pulling the structured signal out of what might look like overwhelming noise. This capability is crucial because it allows us to recover the clean, underlying structure, even from highly corrupted or dynamic data.
Where would that be most useful?
Well, think about robust face recognition, maybe in the presence of sunglasses or a scarf partially covering the face. The underlying face images under varying lighting conditions might form a low-dimensional subspace, making it low rank, and those occlusions are sparse errors. RPCA can help separate the two.
That's incredibly powerful for cleaning up real-world data and extracting meaningful information.
But are there limitations? How robust is it really? Is it computationally feasible?
That's an excellent point. While RPCA in its most general theoretical form is NP-hard, just like L0 minimization.
Ah, okay.
The amazing thing, and what the source demonstrates, is that by using convex optimization techniques, we can often provably and efficiently recover these components, even with noise.
Yeah.
Specifically, you minimize the nuclear norm, which is like the L1 norm but for matrices, acting on singular values to promote low rankness for the low component, and you minimize the L1 norm for the sparse subcomponent simultaneously.
So practical, solvable version exists.
Yes, a convex relaxation that works very well under broad conditions. And this powerful framework extends beyond just background-foreground separation. It applies to other important problems like finding low-rank approximations that utilize only a few original features that's known as sparse PCA, or identifying densely connected communities within very large graphs, a key problem in network science and social network analysis. Okay, so we've identified these underlying structures, sparsity, low rank, and their combinations like RPCA. But when we're dealing with massive data sets, especially for researchers aiming for practical applications, how do we actually compute these structures efficiently? You mentioned convex optimization, but classical methods often buckle under the sheer computational load, right?
You've hit on a critical point. Theory is one thing, computation at scale is another. That's why the focus shifts to techniques optimized for scale. For these large problems, we primarily rely on first-order methods,
Meaning,
meaning methods that, at their core, depend on computing gradients or similar first derivative information. Gradient descent is the simplest and most widely used example. It's powerful because it only needs local information about the function's slope.
but what about things like the L1 norm or the nuclear norm? They aren't smooth, right? They have
Yeah.
sharp corners.
Exactly. They aren't differentiable everywhere. So to handle these non-smooth functions, we use something called proximal operators. Think of them as generalizations of gradient steps for non-smooth functions. For example, the proximal operator for the L1 norm is a function called soft thresholding, which basically shrinks values towards zero and sets small ones exactly to zero. This operation is used repeatedly in iterative algorithms for sparse recovery.
Okay, so we have ways to handle the math, but what about speeding things up even further for truly massive data sets? Just iterating might still be too slow.
Right. So to accelerate computations and handle complex constraints, we bring in more advanced methods. We have accelerated methods like Nesterov's accelerated gradient, which achieve optimal iteration complexity for certain classes of convex problems. Essentially, they converge much faster than basic gradient descent by using a clever momentum idea.
Okay, faster convergence. What about constraints?
For constrained optimization problems, where solutions must satisfy certain conditions, like maybe lying within a specific set methods like the augmented Lagrangian method, ALM, and especially the alternating direction method of multipliers, ADMM, are vital. They are really powerful because they cleverly break down a complex, constrained problem into a sequence of simpler subproblems that can often be solved efficiently or even in parallel.
So divide and conquer, basically.
Kind of, yeah. They alternate between solving for different variables or handling different parts of the objective function. And for truly massive data sets where even computing a full gradient is too expensive, stochastic gradient descent, SGD, is key.
XGD, right? That uses mini batches.
Exactly. It estimates the gradient using only a subset or even a single data point at each iteration. This significantly reduces the computation time per step, even though it might take more steps overall. It's the workhorse behind much of large-scale machine learning. This whole computational arsenal is what brings these theoretical insights to life for large-scale practical problems researchers face.
That's fascinating, covering the computational side. But you mentioned earlier that many real-world problems aren't convex. That seems like it could make things much harder with all those local minima traps. Does this source offer a way around that?
That's where it gets really interesting, and it's a very active area of research. Many real-world problems are indeed non-convex. This means they can have multiple local minima, and standard optimization algorithms can easily get stuck in a suboptimal one.
So finding the best solution is hard.
It can be, theoretically. However, our source discusses how researchers are leveraging insights from high-dimensional geometry and non-asymptotic statistics to understand a surprising phenomenon. Even simple methods, like gradient descent started from a random point or slightly perturbed gradient descent, can often find the global minimizer for many important non-convex problems that arise in practice, particularly in high dimensions.
Why would that happen? It
Right.
feels like you should get stuck.
The intuition is that in very high dimensions, most flat spots or critical points aren't actually local minima, they're saddle points. Imagine a mountain pass. It's flat in some directions but goes down steeply in others.
Ah, okay. So you can roll off a saddle point.
Precisely. While algorithms might slow down near saddle points, they rarely get permanently trapped. Techniques exploiting negative curvature, the directions leading downhill from a saddle point, can help algorithms escape these points efficiently and continue towards a true local or even global minimum. So the geometry of high-dimensional spaces can actually be helpful here.
Okay, let's ground this again. Let's talk about some specific real-world applications where these low-dimensional models and these clever optimization techniques really make a tangible difference for researchers and practitioners.
Absolutely. One really compelling area is magnetic resonance imaging, or MRI. The underlying image of, say, a brain or another organ is known to be sparse or compressible in certain mathematical domains like wavelet transforms.
Meaning it has a simple representation.
Yes. By exploiting this inherent sparsity, techniques based on compressive sampling can significantly reduce the amount of data you actually need to acquire during an MRI scan to reconstruct a high-quality image.
And the benefit is?
Faster scans, sometimes dramatically faster. This means less time in the scanner for the patient, less discomfort, potentially lower costs, and higher throughput for hospitals. The required sampling rate can be much lower than traditional methods dictate.
That's a huge practical benefit, saving both time and improving patient experience. What else comes to mind?
Wideband spectrum sensing is another powerful example, especially relevant for wireless communications. Think about next-generation technologies like 5G and beyond. They aim to utilize underused parts of the radio spectrum more dynamically.
Spectrum is crowded, right?
Very. So the challenge is to quickly detect which frequency bands are active when a vast number of potential bands are available, but only a few might be occupied at any given moment. This signal, the spectrum usage, is sparse.
Ah, sparse again.
Exactly. Compressive sensing allows for stable signal reconstruction, figuring out which channels are active with sampling rates potentially exponentially lower than the traditional Nyquist rates would demand. This enables incredibly efficient monitoring of vast spectrums, crucial for cognitive radio and optimizing wireless resource use.
So listening more efficiently across a huge range of frequencies. Makes sense. It sounds like these principles are everywhere data is, even in places you might not immediately think of.
They absolutely are. Consider something like robust photometric stereo and structured texture recovery. This is a classic computer vision problem. Recovering the 3D shape and surface properties, like reflectance, of an object from multiple 2D images taken under different lighting conditions.
Okay, how does low rank fit in there?
Well, the way an object's appearance changes under varying light often lies in a low-dimensional subspace, which translates to a low-rank structure in the collected image data. Our source demonstrates how methods like robust matrix completion, or RMC, which is related to RPCA, can accurately estimate things like surface normals, the orientation of the surface at each point, and handle real-world challenges like cast shadows and specular highlights far better than traditional least squares techniques.
And you can see the difference.
Oh, definitely. The source shows visual comparisons, for instance, using a textured bust of Caesar. RMC produces clean, accurate, normal maps, these colored images representing surface orientation, while the traditional methods show significant errors, especially in areas with tricky reflections or deep shadows. It's a clear win for these robust, low-rank methods in computer vision and 3D reconstruction.
And you can even use low-rank properties of textures for things like camera calibration. That's really clever. It bypasses some traditional steps, right?
Yeah. Yes, precisely. There's an algorithm called TILT, which stands for Transformation Invariant Low-Rank Textures. It ingeniously uses the fact that many common textures like brick walls, wood grain, fabrics have low-rank properties. It leverages this to estimate and correct geometric distortions in images, like the radial distortion caused by camera lenses.
Around needing those checkerboard patterns.
Exactly. You don't need specific calibration targets. You could potentially calibrate a camera by simply taking a picture of a building facade, assuming it has a reasonably low-rank texture. It streamlines the process quite dramatically.
This all sounds incredibly foundational. It really feels like a bedrock for modern machine learning, and especially deep learning, doesn't it?
It absolutely is. The source makes a strong point that these concepts, these principles, and the computational methods we've discussed serve as a foundation for a more rigorous and deeper understanding of why deep learning works. It's not just about stacking layers.
How so? Can you give an example?
Well, for instance, techniques like dropout used during the training of deep neural networks where you randomly deactivate neurons.
Yeah, a common regularization technique.
Right. It's been shown mathematically that dropout implicitly induces a form of low-rank regularization on the weight matrices within the network. This suggests that these deep networks are, perhaps unintentionally at first, being encouraged to learn low-dimensional representations of the data. And this likely impacts their ability to generalize well to new, unseen data.
That's fascinating. So it connects this fundamental math about low-dimensional structure directly to a practical technique used in state-of-the-art AI. It suggests deep networks aren't just these mysterious black boxes.
Exactly. And we can even take it a step further. We can potentially derive deep network architectures directly from these first principles. The source introduces a concept called minimum coding rate reduction, or MCR2.
MCR squared, okay.
Yeah. It's framed as a principled objective function for learning discriminative representations, specifically for classification tasks. The idea is to find representations that are maximally compressible within each class, but maximally separated between classes.
And how does that lead to a network?
Well, if you take this MCR2 objective and optimize it using a fairly standard iterative gradient-based scheme, the steps of that optimization naturally unfold into something that looks remarkably like a typical deep network architecture. The resulting network, which the source calls a red net, can be seen as more of a white box model.
Meaning you understand why it has that structure.
Precisely. Its components and their functions are derived directly from the optimization of that underlying principle, rather than being purely empirically designed through trial and error. It provides a clear, interpretable pathway from mathematical theory to practical deep learning models.
So what does this all mean for actual classification tasks, like, say, recognizing handwritten digits? Does this derived network work well?
It does. For example, the source demonstrates that for the classic MNIST handwritten digit classification task, a red net derived this way can achieve high accuracy, competitive with more complex hand-designed networks. But what's perhaps even more interesting is how it handles invariances.
Invariances? Like
Yep.
recognizing a 7-8 even if it's shifted slightly?
Exactly. If you enforce group invariance within the MCR2 framework, meaning the classification should be robust to certain transformations like translation or rotation, the resulting ReduNet naturally incorporates this property into its architecture. It learns to be invariant.
So you don't have to specifically train it on shifted digits using data augmentation.
Not necessarily, or at least the core invariance is built in structurally. The source visually shows how images of digits, maybe a 0 or a 1, can be cyclically translated across the image frame, and the ReduNet still correctly identifies them, demonstrating this built-in invariance. It didn't need explicit design for that. It emerged from the principle. This is a really powerful testament to how understanding the underlying geometric and statistical structures can lead to more principled and robust AI.
Wow. This deep dive has truly shown us how pervasive and powerful these ideas about low-dimensional models are. They pop up everywhere, from processing medical images and analyzing networks to understanding the very foundations of modern AI. It's genuinely about finding that hidden simplicity within complexity, and it seems like it opens up entirely new avenues for research.
Indeed. By understanding and exploiting these hidden structures' sparsity, low rankness, and their interplay, we can develop provably efficient algorithms that tackle really challenging real-world problems in this incredibly data-rich era we live in. For researchers, it provides a principled framework, a set of tools to approach problems that might otherwise seem intractable.
So wrapping up, what's a final thought for our listeners to mull over, especially those researchers out there thinking about their own complex data challenges?
Well, if these fundamental mathematical principles concepts like sparsity, low rankness, and principled objectives like MCR2 can not only explain aspects of deep learning, but even naturally derive effective network architectures, what new powerful insights might we uncover if we consistently apply this principles computation applications paradigm even more broadly? Think about all the complex, unstructured data forms we haven't fully cracked yet. What hidden symmetries and low-dimensional structures are still waiting there to be revealed, potentially promising breakthroughs we can only begin to imagine?
That's a great question to leave with, a lot to think about. Thank you for joining us for another deep dive.